Hello, this is the gas laws review video, and if you take a look at this next slide, there are a lot of topics. Seems like a lot, but it's not too bad. We're going to go through these relatively quickly, but there's not much to even look at for each of them. Okay, and we'll start with the kinetic molecular theory of gases. Okay, I apologize for the lack of capitalization in some of these words. Sorry. But anyway, we start with the kinetic molecular theory, and this is just a model to explain ideal gas behavior. So it pretty much details what the traits are for ideal gases. And keep in mind, this is only a theory. That means in actuality, we don't really see gases act like this. It's just a theory of what we want ideal gases to be. And then in the next slide, we're going to talk about real gases, but let me go through each of these right here. So ideal gases, to start off with, they have no volume or no attraction for each other. That means they occupy relatively no space, and when you put two gas particles together, they're not going to be attracted and move towards each other. They rather travel in random straight line motion, so they keep going straight, bump into walls, collide with each other, and when they do collide, they bounce off and energy is transferred. Okay, so even at the molecular level, energy is transferred between objects that collide, and that's something you'll learn later on at the macro scale when you get to physics next year. And then ideal gases also exist under these conditions of high temperature and low pressure. So that's a big one to remember. High temperature and low pressure. Okay. And then they also relatively have low in mass. So if real gases in actuality were to behave like ideal gases, you're going to be looking for the ones that are relatively small in size and low in mass, that's what I meant. Okay. And then here we get into the characteristics and the differences between ideal gas versus a real gas. And so here you could see that ideal gases have no volume, no attraction, but real gases occupy space and they have some attraction for each other. So they don't exactly move in straight lines. They might curve in their paths just to move towards other gas particles because of attraction, forces of attraction. And in terms of size and mass, the smaller they are, the more ideal it is. But the heavier and bigger they are, the more real they're going to be. And that these are the two main things to remember. Oops. High temperature, low pressure, high pressure. Okay, right here. So those are the two main things to remember. The conditions for ideal gas, which is high temperature, low pressure. And then the conditions for real gas, which is low temperature, high pressure. And so when we go into the laws that govern gas behavior, these are the three main factors: pressure, volume, and temperature. And first talking about pressure, this is really the force that is exerted on container walls, so force per area, essentially, if we look at the actual physics equation. But the units for pressure is atmospheres, ATM for short, or kilopascals, which is kPa for short. So these are the two main units we use for pressure. You might see some others, but we're going to focus on just atmospheres and kilopascals. Now for volume, there's milliliters and liters, and then temperature is Kelvin and degrees Celsius. For gas law equations and such, we're looking only at the Kelvin. We only use Kelvin. If you see something in degrees Celsius, you need to convert it to Kelvin. So how do we find the Kelvin? This is on the reference table. So you just simply add 273 to that temperature, okay? And so some of the conversions are like this. So 1 ATM equals 101.3 kilopascals, okay? Volume is 1 liter equals 1,000 milliliters. And then for temperature, well, here's the equation to convert between them, okay? And so there's also something called STP. What is STP? That is standard temperature and pressure. And so you're gonna have to look on reference table A for those values of STP, all right? So when looking for STP values, you need to make sure those units are consistent with the problem. So STP, standard temperature and pressure, are these two values. and standard temperature is 270 Kelvin or 0 degrees Celsius. So you gotta make sure you use the one that's appropriate for the problem. So if they give you a problem where they give you the pressure in kPa, kilopascals, then you wanna keep that consistent. If they give you something in ATM, you keep that consistent as well, use ATM. You don't wanna cross-reference different units, like using ATM when the problem uses kPa, okay? So gotta make sure you keep them consistent. And so now we're going to start going into each of the three gas laws and as well as the combined gas law after that. And so we're going to start with Boyle's law. And this exists when temperature is constant, temperature of the gas. And so here, pressure and volume are inversely or indirectly proportional. What does that mean? So when you increase one value, the other decreases. The same vice versa. When you decrease pressure, volume will increase. So I want you to imagine two containers filled with gas particles. When they're in a larger space, they're more spread out. So there's less pressure on the gas. Versus if you confine them to a much smaller container, smaller volume, they're going to be bouncing off the walls and there's a lot of pressure buildup. Okay? And this graph represents this law. So what happens when you increase the volume? How does it affect the pressure? It's an inverse relationship. It's good to remember this now when you get to physics with me next year. These graphs are important. So inverse relationships have this type of a graph. And so when you increase volume as you go over time, going along the x-axis, notice as you increase volume, pressure decreases. And this equation right here is not on the reference table, but this is the equation for solving Boyle's law problems, okay? The next one we talk about is Charles' law. And so this time pressure is constant, so we disregard that. And we talk about volume and temperature as directly proportional. So when we increase volume, temperature also increases. And vice versa when you decrease it. Okay. Now the graph of this for any direct linear relationships looks like that. Okay. And the equation looks like this. This is also not on the reference table. Lastly, we have the not so commonly used law, Gay-Lussac's law. When volume is constant, pressure and temperature are also directly proportional. So much like Charles' law, one increases, the other increases as well. This is also a linear type graph with an equation like this, just like Charles' law. Alright, so directly proportional, if you increase one, the other increases as well. And then we come into the combined gas law, and this is the one equation that is on the reference table. And it combines the three equations together. And you get something like this. Alright, and how we're going to use this equation to solve those calculation questions on the quiz or any test in the future. So this is the keyword. When a quantity is held constant, you're just going to disregard it from the equation. So for example, if pressure is constant, so when pressure is constant, we're going to disregard P from this equation, and it's going to look something like this. So we just ignore that variable, and we solve it like a Charles' law problem. Same thing applies for the other two. Okay, so when volume is constant, we disregard it. So you have to read those problems carefully. If you don't read them carefully, you're gonna not know what to do. So make sure you annotate those problems, underline, circle values, look for keywords of which is constant so you know what to do. Okay? Otherwise, you're just going to get yourself confused and not know how to solve these problems. Then we get to Avogadro's law. So what happens when we have two different gases, but they have the same temperature and same pressure conditions? That means they occupy the same volume and contain the same amount of particles. So keyword, everything has to be the same here. And here we have a special condition, an STP. So that means 273 Kelvin and 1 atm, or 101.3 kPa. That means 1 mole of any gas occupies 22.4 liters of volume. That means under these two conditions, you get a gas that's 22.4 liters in size, in volume, and 1 mole in quantity. So what is a mole? Let's think about the word a dozen. So we start with this comparison here. 1 dozen equals 12. Well, 1 mole equals this number, Avogadro's number, 6.02 times 10 to the 23rd. So if you say you have 1 mole of something, you have 6.02 times 10 to the 23rd of that specific item. So as our example, okay, so this leads to 1 mole equals 6.02 times 10 to the 23rd particles. So let's say, as our example, we have 1 mole of CO2. That means we have 6.02 times 10^23 molecules of CO2. Now what happens if we have 2 moles of CO2? So if 1 mole equates to that, now we have 2 moles. That's almost like saying we have double the amount. So if you think about it, 1 dozen equals 12. What does 2 dozen mean? 24. So what we end up doing is just doubling it, tripling it if you have 3, the amount, quadruple it if you have 4 moles. So set up ratios, set up proportions, if that helps you to see it visually. Okay? So I'm just going to forego scientific notation rules just for simplicity's sake, but we can see the comparison here between these two quantities. Okay? Now, if you have half a mole, you just half that original number. The only thing you really especially need to remember about the mole is this number, 6.02 times 10 to the 23rd, because that's not on the reference table, so you absolutely need to remember it. And we finally arrive at this very last topic, and that's vapor pressure. So this is pretty straightforward. You just really need to practice your skills with knowing how to read table H. This is on the reference table. So a lot of the problems related to vapor pressure require the use of table H. Okay? And so what is exactly vapor pressure? I should probably talk about that as well. So vapor pressure is really the pressure of the gas particles over the contained liquid. So what does that look like? So I'm going to draw it for you. So let's say we have this beaker that's closed of H2O, okay? H2O, yay! And so we're going to imagine this is closed, so a lid here. So when you have gas particles of H2O, so the higher the temperature, so as you start to heat up, you're going to have more of those liquid H2Os evaporate into vapor, gas form of H2O. And so the more you have that, the higher the temperature, that vapor pressure is going to build up. And once that vapor pressure matches the pressure of the surrounding atmosphere, that's when you reach boiling point. So how do we use this chart then? If you look at this main point, dashed line represents the standard pressure where the boiling points occur. That's important to know. So let's see. As temperature increases, the vapor pressure increases. We're going to follow this line for water, okay? Now, as you increase temperature, vapor pressure increases, so there's a buildup of pressure inside the container until you reach this dashed line. That is the standard pressure of the outside surroundings. So this is when our vapor pressure matches the surrounding surrounding atmosphere. So that means we're going to reach our boiling point. Now, what temperature is that? Lo and behold, it's 100 degrees Celsius. So that also shows why this dashed line is representing the point where boiling point occurs. Okay, so to find the boiling points of these substances, you got to follow the dashed line. Okay, and see where they match up. So propanone is down here. It's approximately 55 degrees, a little bit over that, like 56. Ethanol is a little over here. It's a little past, a little under 80. And ethanoic acid is right here, in between 115 and 120. That's fair. Okay. So a lot of it relies on being able to use this table. Now, if you have any questions, feel free to reach out to me, hmapoy@maspethhighschool.org. Good luck. Don't study too long, otherwise your brain is going to hurt and you're going to wear yourself out. Other than that, best of luck, guys.